The topic of this lecture is indicators. By the end of this lecture, you should be able to explain how indicators work, and you should be able to use their pK values to choose an appropriate indicator for a particular titration. In this section, when we talk about indicators, what we're really interested in are the indicators we use for acid-alkali titrations. And these indicators are usually weak acids. So for example, HN, where N stands for indicator, is a weak acid, so it partially dissociates to give H plus ions and the conjugate base N minus. Now, in order to be a useful indicator, you want the colour of this species here to be different from the colour of this species here. So if you've got a high concentration of H plus ions, so you've got a very acidic solution, the equilibrium will lie to this side and you'll get the colour of this species, the HN. But as you add hydroxide ions and you remove these H plus ions, according to the Chatelius principle, this molecule will dissociate further to replace the H plus ions, hence producing less of the HN molecules and more of the N minus ions, and so the colour will change from from red to green. So we've seen this before when we've used phenolphthalein for our acid-base titrations. So here I've got an acidic solution with some phenolphthalein in it. For phenolphthalein, HN is colourless, but as I add hydroxide ions, more of these will dissociate to more of the N minus, which is pink. So let's demonstrate that. I'll add some sodium hydroxide to this. We see equilibrium shifts and we change from having a colourless solution to a pink solution. Oops. Yep. So at what point does that colour change? Well, according to theory, the balance of colours change from being that colour to that colour at the pH, which is equal to the value of pKn. Now remember, K is just the equilibrium constant for the weak acid. N here just stands for indicator. So pKn is just a negative log of the K value, and that tells you the theoretical point where the colour changes from being predominantly that colour to predominantly this colour. Now, with our puny human eyes, we can't quite detect that change, and we need to see a broader change in the pH in order to be able to detect it with our eyes. And the general rule of thumb is that the colour change, we can detect the colour change when the pH changes from the pK value +1 to the pK value -1. So let's stick with phenolphthalein for a minute. The equilibrium constant for phenolphthalein is 1.26 times 10 to the -9. So from that we can work out what the pKn value is. So pK value is the negative log of the equilibrium constant. So the negative log of 1.26 times 10 to the -9, which is equal to 8.9. So the pH at which the phenolphthalein changes from being colourless to pink is 8.9. But in order for us to pick it up with our eyes, we really want to see the pH change from 7.9 to 9.9. So 7.9 to 9.9 is the range over which we will be able to detect the colour change in the phenolphthalein. Now, phenolphthalein is just one of many indicators. So here's phenolphthalein down here with its colour change range, 7.9 to 9.9. But methyl orange, for example, the colour changes from 3 to 5. Methyl red, 4.2 to 6.2. Bromothymol blue, 5.6 to 7.6. Now, the good news is you don't have to remember these pH ranges. If appropriate, you'll be given them in the question. But you should be aware that different indicators will have different pH ranges over which the colour change is visible. So, how do we know what indicator to use for acid-base titration? Well, that's largely going to depend on how strong or weak the acid and how strong or weak the base is that we're titrating. So let's work through the various options we have. Right, this graph shows how the pH changes as we carry out a titration by adding an alkali, in this case a strong alkali like sodium hydroxide, to a strong acid, for example HCl. So we start off with just pure acid. We haven't added any alkali. Our pH is about 1. As we add the alkali from the burette, the pH gradually increases. And then as we get near the end point, we get this very rapid increase in pH. Now, the change here from a pH of about 3 to a pH of about 11 happens with the addition of just 1 drop of sodium hydroxide from the burette, the smallest increment we can possibly do using the burette. So the pH goes right past the end point, which should be 7, because a strong acid and a strong alkali will produce a salt with a pH of 7. It goes right past that, right through that, with that 1 drop of acid. So we want our indicator to have a colour change in the pH range of in between 3 and 11, in which case it will pick up the end point as we add that 1 final drop of sodium hydroxide. So if we look at our choice of indicators here, in fact all of them would be appropriate. Methyl orange changes from 3 to 5, that's from about there to there. So we'll see that colour change as we add that last drop of alkali. Methyl red, bromothymol blue, phenolphthalein all change colour between that pH 3 and pH 11. So we can use any of these indicators for this titration. Okay, say instead of having a strong acid and a strong alkali, we use weak acids or weak alkalis. So here we start off with a strong acid and we titrate it with a weak alkali like ammonium solution. Now the salt we produce from neutralising a strong acid with a weak alkali will be acidic, so it'll have a pH less than 7. In this example the pH is just above 4 for the end point. Of course that will vary depending on what alkali we actually use. Again, there's a rapid change in the pH when we approach the end point. In this case the pH is changing from about 3 to about 7. So what indicator could we use for this? Well, methyl orange changes from 3 to 5. That probably looks useful. Methyl red, 4.2 to 6.2. Again, that is within the range of the rapid change in pH. So both methyl orange and methyl red would be useful. Bromothymol blue, 5.6 to 7.6. So that's from about there to there. Now that is not within the range of the rapid change of pH. It's gone off to this curve, so that wouldn't be useful. And phenolphthalein from 7.9 to 9.9 is not in this region at all, so that would be useless. So we can use those two indicators but not these two. Now if we start off with a weak acid and titrate it against a strong alkali, our salt will be alkaline, and so we'll end up with the end point will have a pH greater than 7. How much greater than 7 depends how weak the weak acid is. So in this case our rapid change in pH goes from about 7 to about 11. So if we want our indicator to have the pH colour change in between 7 and 11. and we look at this choice of indicators, the only one that has a colour change within the region 7 to 11 is the phenolphthalein. So phenolphthalein. So phenolphthalein would be the only appropriate indicator if you are from this list, if you are titrating a strong alkali with a weak acid. So finally, let's look at titrating a weak acid with a weak alkali. And you see you actually get a very different looking curve here. In this example, the end point has got a pH of 7, and we've assumed that the acid and the alkali are of equal weakness. Under other situations, if the acid was slightly less weak, you might get an acidic salt, or if it was even weaker, you might get a basic salt. But the important thing here is that as you approach the end point, there is not a rapid change. There's not a rapid change in the pH. So in fact, there's no indicator that would be useful for titrating a weak acid with a weak alkali, because the pH does not change rapidly at the end point. Now we need the pH to change by at least 2 units in order for our indicator to work correctly. So the thing to take away is that there's no suitable indicator for a weak acid against a weak alkali, since the pH does not change rapidly at the end point. If you were doing this titration, you need to use a pH meter. Indeed, a pH meter could be used for any of the titrations, but pH meters are expensive, they're very fiddly and time consuming to set up, so I would much rather use an indicator. So you should have the knowledge now to choose an appropriate indicator for any given titration, depending on whether or not the acid alkalis are weak or strong. Just want to show you a question from, I think it was from last year, the 2016 paper. It says the use of an indicator is not appropriate in titrations involving A. hydrochloric acid and methylamine, B. nitric acid and potassium hydroxide, C. methanoic acid and ammonia, D. propanoic acid and sodium hydroxide solution. So pause the lecture, have a wee think about that and decide what the correct answer is. Okay, let's look at the options. Hydrochloric acid is a strong acid, methylamine is a weak alkali. You know that because it's listed in your data booklet as a weak base. So strong acid, weak alkali, yeah, we can use an indicator. The endpoint will have a pH less than 7, but we can still use an indicator because there will be a rapid change in the pH near the endpoint. Nitric acid, potassium hydroxide, strong acid and strong alkali. Large increase in the pH near the endpoint, use an indicator. Methanoic acid and ammonia, well, carboxylic acids are weak acids, ammonia is a weak alkali, so weak acid v weak alkali, there's no suitable indicator to use for that titration, so the answer would be C. By now you should be able to explain how indicators work, and you should be able to use the pKin values to choose an appropriate indicator for a particular titration.